How to design a squaring function circuit and its analysis with temperature compensation are explained in this 217th video in the circuit design playlist. As shown, the input voltage Vin is between 0 and 10 volt in this design, and the output voltage at the output of the second op-amp is related to input in the form of Vout equal to 0.1 times Vin squared. We want to see how this circuit is working. There are two op-amps, op-amp 1 and op-amp 2, and these two op-amps are recommended to be in the same package. For instance, as a recommendation, here are examples of op-amp from Texas Instruments, for example, OPA 1556 or let's 1656 and 1655 could be the options depending on whether we want to dual package or not. The nice thing about that is it's ultra and low noise and low distortion FET-Input operational amplifier. So especially for 1656, that is the dual op-amp, is highly recommended. If interested, other choices could be, for example, from Analog Devices, the op-amps and two package op-amp, let's say AD8092, or let's say from Texas Instruments, OPA 607 and OPA 817 and OPA 855, depending on how much budget is allocated to the selection of op-amp and depending on the gain bandwidth target for the op-amp. So if just a good op-amp is desired, one example, as I said, is the Texas Instruments OPA 1656 that has two op-amps inside one package. Also, we can see that in the design we need to have 4 bipolar junction transistors that need to be matched, especially or at least TA1 and TA2 need to be matched with each other, and then TB2 and TB1 need to be matched with each other at least. The best scenario is when we can have all 4 transistors in one package as matched transistors. For example, the famous Math 14 package from the Analog Devices is a matched monolithic quad transistor package, which is exactly what we need for this project. This is one good choice, but if that is not available, there are other packages of either dual matched transistors or quad transistors as well. Okay, with the choice of components discussed, now let's talk about resistors. The nice thing about these resistors is they are specially selected to be streamlined 100 kilo ohm for almost all resistors in this circuit. The only little catch is they need to be 1% low tolerance resistor. For 2K, a 5% is all fine, but then I recommend 1% as well. So now let's analyze. So at the base of the transistor TA2, we have the ground connection, so it means the voltage of base is 0. At the base of TA1, we have a ground connection, it means it's 0 volt as well. Now, we can see that via two base emitter drops, so base emitter of TA1, VBE, let's say A1, and then base emitter of TB1 transistors, which refer to it as VBE, let's say B1. We get to the common emitter in this design, so I'm going to refer to this as node E. Okay, the same thing about the base emitter drop VBE of transistor A2. From 0, we get to roughly negative 0.7 volt to the base of transistor TB2, and then from there, another base emitter drop will get us down to, again, the common emitter node. So I can write a KVL across this route. So if I do that, so I'm going to write KVL, and my KVL is basically saying voltage of base emitter for transistor A1 plus the voltage of base emitter for, let's say, the transistor B1 is going to be equal to the voltage of base emitter from 0 A2, so I'm going to write it voltage of base emitter to A2, and then plus the voltage of base emitter for transistor B2. So there you go. Okay, so this is the KVL or Kirchhoff Voltage Law or equation that I can write. Now, I need to use the famous Shockley PN Junction diode equation, which basically says that what I can write is voltage of base emitter is equal to thermal voltage, which is KT over Q, roughly about 26 millivolt in room temperature, and then times natural log of roughly collector or emitter current of the transistor divided by saturation current. Okay, so what I'm going to do is I'm going to just substitute the base emitter voltages in the KVL equation with this Shockley diode equation that I have. So if I do that, basically combining equation 1 and equation 2, I am going to get, let me use a different color. So combining these two equations, I'm going to get, I think it's better to just write it here. So I'm going to just write it here. So equation 1 and equation 2, if combined, then I am going to substitute for base emitter 1, and I'm going to get VT, which is roughly the same for all these transistors because they have the roughly same junction temperature, but I'm going to just talk about it in more detail. So VT, which is again KT, and remember K is Boltzmann constant, and Q is the electron charge, 1.6 times 10 to the power negative 19, and T is the temperature of the junction, so junction temperature in Kelvin, which if you're in room temperature, it's going to be roughly 290 degree Kelvin, between 290 and 300 for room temperature. Okay, so with that said, let's just substitute back to equation 1 and substitute for voltage of base emitter. So VBA1, VT, natural log the current of collector A1 divide by saturation current transistor, let's say A1. For base emitter, so B1, basically for this transistor here, the same thing. I have VT, natural log, and then I have ICB1 divided by ISB1. So ICB1 is this current, which is, so I'm going to write it, ICB1, and the other one is ICA1. So these two currents are roughly the same because these two transistors are in series, and roughly they have the same so emitter current. So I would say in this case we can just say basically these are I in and I in, because as you can see this IC, so this ICA1 is coming from this branch shown, and obviously there is no current that can flow here because we are assuming that op-amps is ideal op-amps, so input impedance is infinite practically. So basically that means the current here is 0, and therefore whatever current is coming from input route is going through the ICA1, and I'm going to refer to it as I in for the design. So that's I in. That's why I refer to these ICB1 I in and ICA1 I in the equation. Now equal to, on the other side of equation 1, I have again VT or thermal voltage, and then natural log I have ICA2, so I am going to write here as ICA2. Let me just write it here, ICA2, and then that's roughly the same as the emitter. We are making the assumption these transistors have high current gain or high beta. So beta is much larger than 1 for these transistors. Therefore, as a result, we can make the assumption that the current of the collector and emitter are roughly practically the same. So, but I'm going to write ICA2 divided by ISA2. And finally, for the last one, which is VBE2, for this one, I'm going to write the same thing. Voltage of thermal or thermal voltage, natural log ICB2, and then we have ISB2. And recall, ICB2 is this one. So here is ICB2. But again, because we make the assumption that the op-amp is ideal, the input impedance, so input impedance is, I'm going to refer to it as, let's say, Zn, or input impedance of op-amp is approximately infinity, very large, especially if we select FET input op-amps, and therefore whatever current is coming from output via resistor or through resistor 100K is going directly toward the route of ICB2. So that's going to be I out, or simply IO. So I out or IO. Okay then, so ICB2 is I out, and ICA2 is, just keep it as ICA2 for now. So I'm going to write that this is ICA2, and here is also ICA2. As I said, the current of emitter and collector are roughly the same. Now, the nice thing is I can cancel out voltage of terminal voltage from all sides, and because I have sum of bunch of natural logs, I can just simply write them like this. So it's going to be natural log ICA1, which is IN, times, so IN times IN. Okay, so IN times IN, divide by ISA1 times ISB1 equal to. On the other side, I have the sum of two natural logs, so therefore I can write it as natural log of ICA2, so ICA2, and then times, instead of ICB2, I'm going to write I out. So I out, divide by ISA2, the saturation current, times ISB2. Now, here is the nice part about the packaging. So as I said, in the design to be able to function as we are planning, the TA2 BJT transistor and TA1 BJT transistor need to be matched at least. The same thing with TB2 and TB1 need to be in the same package and matched. If that condition is satisfied, then because of matching, basically what happens is ISB2 and ISB1 will cancel out each other because they are equal from both sides of this equation. They just cancel out each other. And then with the same line of thought and reasoning, then ISA2 also cancel out ISA1 because they are equal. That's the main reason we needed them to be basically matched transistors. When we say transistors are matched, it means the two transistors are on the same basically substrate in the same package, so therefore their junction are benefiting from very close properties, therefore the saturation currents are equal. The concern about that is the saturation current in the diode equation, this is a function of temperature, so is related to temperature, proportional temperature to the power 3. So it's very powerful function and sensitive function of temperature. We want to get rid of it because otherwise our design will be very much temperature dependent, and that's the reason we had to have the matching so that we get rid of the saturation current and therefore a considerable amount of temperature dependency. Now we have an equation that on two sides of it we have natural logs of arguments equal. So therefore, because of the properties of logarithm, which means it's a one-to-one function and just basically increasing function, absolutely increasing function, so we can just say there's a one-to-one relationship, and hence I in times I in, which is I in squared, should be equal to ICA2 times I out. So I'm going to write it exactly like that. I in squared should be equal to, therefore, ICA2 times I out. Or basically, in summary, I can say I out is equal to just I in squared divided by ICA2. Now, let's substitute further. Okay, what is I out? Well, I out is the current going through the 100 kilo ohm resistor here. So that means because the op-amp is ideal and operating in linear region, not saturated, since the positive terminal of op-amp 2 is connected to ground, so the voltage there, assuming a zero drift low noise op-amp, the voltage there is practically 0 volt. Because of the negative feedback via this resistor, this op-amp is going to enforce the virtual ground, and therefore the positive terminal being 0 volt will result in negative terminal also be 0 volt as well. So now what happens is the voltage drop across the 100 kilo ohm is purely just V out, because on one side is V out, on the other side is 0. Therefore, we can write the equation for I out. I can say, I'm going to write it here, I can say I out is simply V out divided by 100 kilo ohm. Okay, good. What about I in? I in, we have the same basically sort of reasoning, and that's going to be what I'm going to show you. So I in is roughly equal to, okay, so the same thing about op-amp 1. It is operating in linear region, not saturated, with positive terminal or non-inverting terminal is grounded, and therefore assuming a zero drift and well-compensated op-amp, it would be 0 volt. And again, because of the negative feedback and force in the circuit, therefore op-amp 1 will also enforce virtual ground, which means then since positive terminal is 0, then negative terminal gonna be 0 volt as well. So therefore we have 0 volt across for the negative terminal. That means the voltage drop across the 100 kilo ohm is basically just V in on one side and the other one 0, so it means we have plus minus V in drop across the 100 kilo ohm. So as a result, obviously we have I in equal to V in divided by 100 kilo ohm. So I'm going to just use that here. So I in is roughly V in divided by 100 kilo ohm. Okay, so I agree that the remaining part is ICA2, which is the current of the collector or emitter of transistor TA2. What about that? Okay, that's not difficult, but there's a little nuance as an interesting thing about that ICA2. So let's deal with that. All right then. So I am going to talk about ICA2. And let's refer to this whole thing that we got here as, let's say, equation 3. So for ICA2, I have one interesting outcome. ICA2, which is, as I said, roughly the same as IEA2, or current of the emitter of transistor A2, is equal to. Now, take a look. I'm going to make the assumption, and I'm going to show you that why that assumption is valid, that the current that goes through the base of transistor, the current of base of transistor TB2 is very small. So this current here is super small. So I'm going to assume this current is negligible compared to the current of ICA2. So therefore, I can make the assumption that ICA2 is the current that is going this way as well, so downward. Now, obviously at this node we have a KCL, which means I have current I1 going through resistor R, and I have current I2 going to another resistor 100K, and the sum of these two should be equal to ICA2. So is equal to so ICA2 or IEA2 is equal to I1 plus I2. Now let's write that down. What is I1? I1 is the current of resistor R, and obviously that means on one side we have the regulated, super important, regulated negative 10 volt supply, regulated because we need the accuracy for the, so that we get the accurate output voltage equation that we are looking for. So therefore, with the regulated negative 10 on one side, what we have on the other side of the resistor R is just a voltage drop from 0 to this point, which means the voltage here is roughly negative 0.7 volt, the nominal voltage of the base emitter of a functional and operational BJT transistor. So, but I'm going to just refer to it as voltage of base emitter. So it's roughly, as I said, negative 0.7, but it's basically just VBE-A2 negative. So I'm going to just write it this way. I1 is negative VBE-A2. That's the top one. And then on the other side, we have negative 10 volts. So it will be minus or negative 10. There you go. Minus negative 10. And then that's the voltage drop across the 100K. So I'm going to keep it as 100K. What about I2? I2 is now the voltage, the current through the 100K that is shown here, which is exactly the 100K across the base emitter of transistor TB2. So I'm going to just simply write VBE, basically B2 divided by 100K. And these 100Ks, as we said, they need to be 1% accurate so that roughly they are both 100K. That minimizes the error in the system. So as a result, I get basically ICA2 is equal to now VBE B2 minus VBE, so let me just write it better, minus VBE A2 divided by 100 kilo ohm. So what I did is just combining basically these two together, keeping them together, and then keeping this separately. So it's going to be now it's going to be plus then 10 volt regulated divided by, so 10 volt divided by 100K. Okay, you see the picture right now. So the beautiful thing about putting this 100K resistor here is additional temperature compensation. And that is clear here. So you can see these two base emitter voltages of A2 and B2 are trying to cancel out each other, and they are roughly both about 0.7 volt. Not exactly, but they are roughly 0.7 volt. The difference is a minor error, which is decent for the design, meaning that it sort of helps us to say ICA2 is roughly then 10 volt divided by 100K, because this thing here is roughly 0. Not exactly, because there will be some millivolt difference between the voltage of base emitter of transistor T2 and the voltage of base emitter of transistor A2, not only just because of the delta in temperature, which can be minimized assuming 4 transistors are in same package and on the same substrate, but the current of these transistors are slightly different. So there will be a slightly difference in their base emitter voltage, but that's going to be very minor. You're talking about, say, few millivolt or 10 millivolt over 100 kilo ohm, which is pretty small number. So I can make the assumption that this thing, as I said, is roughly 0. And therefore it goes away. As I said, it's as if you have 10 millivolt divided by 100K, which is basically 10 to the power minus 7. So you're talking about 1/10 of a microamp, 100 nanoamp, or even less. While, of course, this component here, 10 volt over 100 kilo ohm, this is basically just 100 microamp. So let me just make sure I'm not missing something. So 10 volt divided by 100 kilo ohm is going to be, so let me just double check. Yeah, this is going to be 100 microamp. So on one side for this component, we have 100 microamp. And for this one that I just showed you is less than, say, 0.1 microamp. So obviously it's on the order of 1,000 times less than the reference current. So it's negligible and we can drop it. So we can just drop it. Now, this 100 microamp is our reference current, basically, because it's a constant and it's well compensated temperature-wise. So reference current, or IREF. So what I'm trying to say is this ICA2 basically is our IREF. So I can say, therefore, ICA2, or simply I reference, is equal to 100 microamp in this design. So the whole idea is we have a well-regulated 10 volt, and with the scheme we have with these two resistors, especially with these temperature compensation resistor, we sort of get rid of dependency on base emitter for the reference current, as we saw, and reference current is 100 microamp in this design. I'm going to substitute that back into equation 3 when we have ICA2. So I'm going to use this, name this as equation 4, and I'm going to just say equation 3 and 4 considered together, it's going to give us then I out, which is I out here, and it's V out over 100K is equal to I in square, which is V in over 100K square. So V in over 100 kilo ohm squared, divide by, and we have ICA2 in denominator, which we just discussed, is IREF, which is 100 microamp. So IREF, which is 100 microamp. So putting that all together, then V out becomes equal to V in squared, divide by 100K. So for 100K we have power of 2, that cancel out, at least one power cancels out with the 100K here, so it leaves us with another 100K. Okay, and then we also have the reference current here, which is 100 microamp. So it's going to be just, let me just make sure I'm not missing something. Okay, then, so we get, therefore, as a result of this, we have, just making sure, so IREF is 100 microamp, and then it's the, okay, so what's going to happen is we have 100 microamp there, which is 10 to the power minus 4. Got it. Okay, then, so we have 100 microamp. And now, finally, substituting everything, we are going to get V out is V in squared. So we have 10 to the power 5 times 10 to the power minus 4, which is exactly what I was chasing to see, which confirms the final outcome as we were chasing, is basically saying we have 0.1 times V in squared. That's the relationship between input and output voltage realized by this circuit. So I hope this circuit and its analysis is interesting and helpful in terms of how we can potentially realize and implement a circuit that realize and implements the squaring function for us using just 2 op-amps and 4 bipolar junction transistors. Again, if you're interested in choices for transistor and op-amp, I recommend MAT14 quad matched transistors from Analog Devices or similar ones that are available. And then also I recommend OPA 1656, a dual op-amp package from Texas Instruments, and other examples that I discussed as well. I hope this video is helpful and you find it interesting. Thanks for watching.